Alright, hello guys. Today we're going to be looking at a variation of a rather famous physics problem about a flying pig. What we have given here is that a pig flies in constant circular motion. Its flight path is a circle parallel to the ground, and those are important things to think about because it will shape how we go about this problem. Given that the mass of the pig is 0.155 kilograms and the length of the string is 0.9 meters and that the period is 1.8 seconds, we're going to have to determine the tension of the string, the angle formed of the horizontal, and the velocity. Over here we have a picture to help visualize what's going on in this situation. This dot here is the pig, which is suspended by a string, and it flies in constant circular motion, so it's moving, the velocity at which it moves is constant the whole time, and it moves in a circle like this, which is parallel to the ground. Over here you can see a free body diagram which displays the forces which act upon the pig. So we have a force of gravity, which as always just points straight down. We have a force of tension, which is the tension from the string, which acts upon the pig. And we also have this centripetal acceleration, which is what causes the motion to be circular. All right, to solve this problem, we're going to be setting up a system of equations which are going to mainly revolve around the components of this force of tension. Over here, you can see that we've drawn two dotted lines, vertical and the horizontal, to show that there are the two components of tension which we're going to be breaking it into. And here, this is the string, and this is theta, which is the angle formed between the string and the horizontal. All right, to start off, we're going to look at just the vertical part of this problem. Vertically, we know that there's this force of gravity, which is pulling it down, and part of this force of tension is pulling it up. And we know that its net vertical movement is going to be 0. So that vertical aspect of the force of tension is going to be equivalent to the gravity because they're going to cancel each other out and it's not going to be moving up or down. So using F to represent the tension in the string, we can say that F sine theta is equal to mg. And we know that because mg is just the force of gravity and F sine theta is the vertical component of this tension here. All right, next, after we've done the vertical, we're going to have to look at the horizontal. Horizontally, we know that the horizontal component of this tension is going to be providing this centripetal acceleration because those are the only forces going in the right direction. So we know that we used F sine theta here, so we're going to be using F cosine theta here to represent that this is the horizontal aspect rather than the vertical aspect of the tension. And the centripetal acceleration we know is equal to mv squared over r. And we know this because centripetal acceleration is always equal to v squared over r when you're in constant circular motion. And that's the acceleration. So using the Newton's second law of F equals ma, we can know that the force is equal to m times that acceleration, which yields us the equation F cosine theta equals mv squared over r. All right, then for our next system of equations, we're going to use one of those. It's a little more simple. We're going to say r is equal to L cosine theta. And this is a little less difficult to come up with than the other ones, because all this is really saying is that this radius here is the cosine of the length of the string. It's pretty simple to think about. It just shows that the length of the string determines how large of a circle it's going to be making. And lastly, we're just going to say that the velocity is equal to 2 pi r over t. And we can say that because that's saying that 2 pi r, which is the circumference of the circle, that's the distance it goes, over t is the time it takes it to go. So velocity is just distance over time. So we're making our distance one circle rotation, and our time just the time it takes it to make that one circle rotation. All right, and now that we've set up this system of equations, we can go about solving it. So right away we can see over in this second equation here, F cosine theta equals mv squared over r. We have this v, which we already have something we can substitute in for v. So we're going to start by substituting v into this equation, which is going to give us F cosine theta equals m times v squared. So that's going to be 2 pi r over t. That's squared all of that divided by r. Just a little bit of algebra to straighten out this equation. So multiplying out the square of the 2 pi r over t is going to give us 4 pi squared r squared over t squared, and all that over r. So we're going to cancel out one r, which is going to leave us with m 4 pi squared r over t squared. All right, for our next step, we're going to take this even further and see that this r here, we already know how to have something we can substitute in for r. I apologize that one of the r's is capitalized and one is not. But we can take that f cosine theta, and we're going to plug in L cosine theta for r. So that's still the m 4 pi squared. But now for the r, we're going to plug in L cosine theta, and all that is still over t squared. Now this equation is just about where it needs to be. We see that we have the cosine of theta on both sides, so that can be canceled out, leaving us with just f equals m 4 pi squared L over t squared. And now you can see here that we have no more constants that we don't know. So we can solve for tension, plugging in our 0.155 for m. 4 pi squared is always the same, and L being 1.8, or L being 0.9, and T being 1.8. We can plug everything in there into a calculator, and that will give us that our tension is equal to about 1.7 newtons. All right, having solved that our tension is 1.7 newtons, we're going to go looking for the angle next. So we know that F sine theta equals mg from our system of equations that we found before. And so now that we know F, we can have the rest of the things and we can solve for theta. So plugging in our 1.7 for this force here and plugging in 0.155 for the mass and 9.8 for gravity, we can throw all that into a calculator and find that our theta here is going to be equal to approximately 63.3 degrees. And when using your calculator, make sure that you're in degrees, not radians. Otherwise, you might get an answer that doesn't really make sense. And for the final part here, we're going to determine the velocity. So going back to our system of equations, we know that the velocity is equal to 2 pi r over t. And that having all the information that we do now, we can solve this pretty easily. So we're going to start with the velocity, and we're going to change that r into L cosine theta. So we get velocity equals 2 pi times L cosine theta over t. And then we're going to plug in everything we know. So we have the 2 pi here, our length, which we know is 0.9, our cosine of the angle, which we now know is 63.3, and all that over t, which is 1.8. And plugging everything in like that, we're going to get our velocity is going to be equal to about 1.41 meters a second. Now we've found our tension, our theta, and our velocity, and that's all we're needed to find. So I hope you guys enjoyed this walkthrough of this flying pig physics problem, and I'll see you guys soon.